Hi, I'm Mattias Halloran from St. Paul, Minnesota. Imagine if we could turn a deadly molecule into a precise trigger for drug delivery, enabling the first ever therapeutic treatments for a condition that kills millions. This is what I set out to do, develop Hemin-Activated Lipid Nanoparticles for targeted drug delivery in hemorrhagic stroke. Hemorrhagic stroke, specifically intracerebral hemorrhage, or ICH, is a condition described by hemorrhaging, or bleeding, right into the brain. What's particularly dangerous about ICH is that blood in the brain starts to break down over time into a molecule called hemin. In healthy blood, hemin is bound to hemoglobin and helps carry oxygen all over our body. However, after hemorrhage, red blood cell breakdown and oxidation generate free hemin, which breaks down neuronal lipid membranes through something called lipid peroxidation, ultimately resulting in cell death. I like to think about it like the blood is slowly eating away at our brain, breaking down membranes and killing neurons. This is why, unfortunately, nearly half of patients die within 30 days of hemorrhagic stroke. But what's crazy is that there are no pharmacological options to treat blood breakdown, despite over 3 million people dying in 2021 alone. Researchers have experimented with treatment options, and one of the most promising actually appears to be a protein found in our own body called hemopexin. Hemopexin binds very strongly to hemin and clears it from the hematoma, basically preventing it from eating away at our brain. The issue is that we don't have enough of it during a stroke, so scientists have experimented with supplementing our bodies with more. And in fact, in rat models of ICH, scientists increased brain hemopexin and it reduced the hematoma size by approximately 45%. However, there's a serious timing issue with hemopexin that prevents translation into humans. Hemopexin has such a high affinity to hemin that in the early stage of stroke, where hemin is still bound to hemoglobin, hemopexin rips hemin from hemoglobin and causes oxidative injury, proven to increase neuronal death as demonstrated in the stage 1 part of the diagram. In contrast, late dosing misses the window entirely. But since doctors have no clue to what stage patients are in, they never know whether administering this potentially life-saving drug could help or harm the patient. I approach this problem through the lens of nanoparticles. Lipid nanoparticles are small lipid bubbles that help carry cargo and are deployed in a wide range of therapeutic targeted drug delivery applications. I hypothesized that we could exploit how this microenvironment, particularly hemin, degrades lipid membranes in stroke, just like the ones in neurons, to then degrade the membrane of the nanoparticle itself. The nanoparticle would remain stable in physiological environments and the early stage of ICH, where treatment would actually harm the patient, but then release its therapeutic cargo exactly where and when it's safe. To build these nanoparticles, I used an ethanol injection, a common method for preparing liposomal nanoparticles. The lipids are dissolved in high purity ethanol and are injected into an aqueous solution containing a cargo, in my case, a bright pink fluorescent dye called SRB. The nanoparticles form spontaneously upon injection, encapsulating the bright dye, allowing me to detect whether they've been burst open by observing an increase in fluorescence readings. To enable release only in conditions high in hemin, I utilized two strategies. I first incorporated polyunsaturated fatty acids, or PUFAs, into the membrane composition. These are the types of lipids found in neuronal cells that can be degraded by hemin. I selected PLIPC 18.2.16.0 for its existing use in lipid peroxidation studies and relatively low baseline leakage compared to the more aggressive alternatives. Secondly, I developed a hemin-binding peptide based off the IRP2 hemin binding motif found in our own body, which is evaluated to have the highest binding affinity, around 0.58 micromolar Kd. The peptide does two things. Firstly, it enables hemin recruitment right at the nanoparticle surface, and two, catalytically activates hemin into a high-spin state perfect for lipid membrane degradation. The peptide was supported using HemoQuest computational modeling to preserve binding affinity and pentacoordination critical to this catalytic activation. Nanoparticles also consisted of 45% molar content cholesterol and DSPC to provide a strong structure for tuning down the line. I then tested multiple different amounts of these PUFA and peptide ingredients in nanoparticles and recorded their baseline leakage and hemin-triggered release in an in vitro model of hemorrhagic stroke. I then fed these data points into a response surface model to determine the formulation that maximizes hemin-triggered release while minimizing baseline leakage. I then built that optimal formulation and evaluated it in hemin and baseline conditions, plus a 50 micromolar hydrogen peroxide condition that simulates the early hemorrhagic microenvironment where drug nanoparticle release would actually harm the patient. Based off the model and demonstrated on the graph on the left, I found that a 24.5% PLIPC PUFA and a 6.3% peptide functionalization was the optimal formulation for selective hemin-triggered release. The model demonstrated an R-squared value of 0.849, which indicates that it's a strong predictor of the optimal formulation based off the data I fed it. The optimal formulation demonstrated, on average, just 8.9% baseline leakage in physiological conditions over 75 minutes, but over 43% release in hemin, nearly a 5-fold jump in release. That's a 4.88x selectivity ratio, meaning that the nanoparticle releases only when hemin is present. A one-way ANOVA with a 2-key post-hoc analysis demonstrated that hemin release was statistically significant for both baseline p less than 0.01 and ROS. Also, importantly, the optimal formulation demonstrated a 50 micromolar hydrogen peroxide release, which again models this early ICH environment in which you do not want the drug to release, that was not statistically different from baseline leakage, evidenced by overlapping error bars in the right figure and a p-value of 0.2875. This means that the nanoparticle would remain stable at rates statistically similar to normal baseline leakage, even in the early ICH conditions where drug release would harm the patient. But what does this all mean, and why do you care? Well, this study proves that hemin-mediated lipid peroxidation can be exploited as a precise trigger for spatially and temporally selective drug delivery in hemorrhagic stroke conditions. But more importantly, the platform could enable safe hemopexin administration, offering the first pharmacologic treatment to millions of ICH patients annually. Right now, nearly half die within a month, and survivors face severe disability and we have nothing to offer them. But this platform could change that. Several limitations should be noted, however. The central composite design did not include 2 star points, and the final optimized trial was evaluated in n=2 due to lipid material constraints. Additionally, this work was performed using a surrogate dye in vitro conditions. Essential steps should include loading hemopexin into the nanoparticle and evaluating and confirming selective therapeutic performance in vivo ICH models, for example, zebrafish. But if those pan out as this data suggests, millions of patients may finally have an option for treatment. Thank you for watching.